Ready?
Good afternoon, everyone. Up till now, we have completed quite big portion of chapter superconductivity in your syllabus, and in continuation with this, we are going to discuss today application of superconductor. Up till now, we have discussed certain points. Let's revise the things so that you will get a continuity. The things up till now we have discussed, they were concept of superconductivity, temperature dependency of resistance of material, then properties of superconductor. There are several properties we have divided into mechanical property, electrical property, if you remember. Then types of superconductor, type 1, type 2, soft superconductor and hard superconductor, if you remember all those things. Okay, then if we move further, we talked about a high temperature superconductor, that is superconductivity at higher temperature, that is at about 78 Kelvin temperature. So such kind of things we already discussed, and if we are able to get quite good material which are showing superconductivity at high temperature, then it is going to solve our problem in future also. And right now also we are having quite many application based on superconductivity. So we are going to discuss those applications today. Among them, I have divided into certain category, and very first division of application, that is electrical applications, that is falling in the branch of electrical engineering and related to them. In electrical engineering, we are having a two part. If we are studying the electrical engineering, first one is generation of electricity, and then second is transmission of electricity to the needed places. So in first part, if we say generation of electricity, there are several problems related with the generator. You have already studied the concept of dynamo and generator. Both are working on a principle of Faraday's law or induction phenomena. In both the phenomena, in both the devices, we know that due to certain kind of effects or laws, there are losses involved in that, and one of them is copper losses. When we talk about a dynamo or generator, copper losses, copper coil is wound in that, and the flux is going to change related to that or linked with that, and due to that EMF is induced according to the Faraday's law. But in those current or the change in flux will result into current also, and that current will create a problem with the resistance when we say I square RT, Joule effect. So as the current increases, I square increases, and the coil is going to show resistance, and due to that loss will be there. On the other side, eddy current losses are also there. Then due to hysteresis losses are also there, that you already studied in 12th standard. So how to solve that problem when we are generating the electricity? And the solution is, if we are using a high temperature superconductor in place of such kind of normal material or copper material we are having. So in that application, if we make out a generator made up of superconducting coil rather than copper coil, normal copper coil, if you use superconducting coil wound in the dynamo or in the generator, then in that case it will show least resistance or zero resistance. As we already studied in a property of superconductor, it is going to offer zero resistance. So due to that, there won't be I square RT, Joule effect, and due to that there won't be any energy loss when we are generating it. So this is the one diagram, it is shown there, and components are also mentioned there. But within that, if you see carefully, within generator part, we are having a helium, liquid helium, which is passing through the tubes, and in that case it is going to take out the energy, heat energy, which is produced within the generation process. And as the temperature is going to decrease, and if it goes further below than the critical temperature of the coil or the material used for making coil, then in that case it will be converted into superconductor, or it will get a state of superconductivity. So there won't be any resistance available, and due to that there won't be any loss related to that. And by making all such kind of application of superconductor in generation, we can have two more benefit. One is size of the generator, that is quite small compared to the normal generator, and weight of the generator is also very small, so that transportation or mobility problem will be also solved. So these are the advantage we are getting in a part of generation of electricity with the help of superconducting coil in a generator. And it is not only talk, but it's already done by the institute. Here it's a given example that it's available on the site of the institute, that they have already tried a 4 megawatt generator with the help of Siemens company and Karlsruhe Institute of Technology. They have designed such kind of superconducting generator, which will create a electricity, and that electricity with a, we can say, least loss in that. Otherwise normal conductor dynamo or generator, they are creating energy, but along with that they are taking out about 20 to 30% energy and they are converting into heat. So here there such kind of losses won't be there. In future, if we are using such kind of generator, then in generation of electricity, whatever losses are there, that we can reduce and we can have more better, we can say, energy solution of energy crisis. The second portion is, after generation of electricity, we don't keep it over there only, but we need to transfer it to the needed places. So if we transmit it from one place to another place, again, because here the R factor, resistance, is depending on resistivity, length and cross sectional area. In that, length makes a difference over here, because from the power generating station or power station to the place, the distance is quite far, and due to that L becomes large, and whatever material you are using and resistivity is whatever the small amount is there, but then also due to large value of L, R is equal to rho L upon I. In that case, resistance increases, and due to that increase in resistance, and on the second end where we are having an application which is drawing a large current, in that case I square also increases, R also increases, and due to that Joule effect, as you know the equation, I square RT, the resultant energy is distributed in terms of heat. So up till now whatever the data was observed, and from that it is observed that 10 to 15% of energy generated, that is dissipated in terms of heat energy due to this kind of losses in the transmission lines. And we cannot have any solution, because we cannot shift the places or industrial area. We cannot set up the power plant within the we can say neighboring of civilization, and due to all such kind of problems, we don't have any such solution up till now. But now we are as we are putting the superconducting material into the real practice, so we can have solution of such kind of problem also. And this is not a just a hypothetical thing, but it is already implemented. So this is the one of the example. The prototype they have made, a prototype superconducting transmission line, they have made it. Brookhaven National Laboratory, they set up such kind of thing, and they transported about 1000 megawatt energy into, we can say, premises of 40 kilometer, and the total amount transported, if they have connected with the power plant, and total amount of energy generated over there, and that will be transmitted with the help of such kind of superconducting grid. And when it was compared with the normal arrangement, then what kind of differences it is going to bring? That one of the thing is, in normal circumstances, when we are using alternate current as a transmission media, and we are changing sending it in terms of alternate current, then in that case we need a big transformer, as well as step up step down transformer kind of thing, as well as high volt transmission links we need it. And in those cases there are certain problems are arising in transmission also. Transformer, they are also creating quite many kind of losses. So those losses can be reduced, because here we are not sending it in terms of alternate current, but we are going to send it low voltage DC direct current manner, and due to that losses will be reduced. And this is much more we can say a better manner compared to the normal AC transmission with the normal material, that is aluminum or copper conductors. Same way, optonics energy industry and Subu Universities of Superconductivity and Sustainable Energy Center, they have also conducted one small experiment in 2010, and they have established such kind of transmission line, superconducting DC power transmission line, and they have also observed such kind of comparison or differences between the two lines whatever we are using. So if we use a direct current superconducting grid, in that case the loss will be less compared to the alternate current superconducting grid, and both are smaller or both are lesser compared to the ordinary conducting wire alternate current loops or transmission lines. So if we see that scenario, then compared to the normal conductor grid we are having right now, the alternate current grid with the superconductor, that will be beneficiary, and if we are using a direct current transmission with the help of superconducting grid, that will be much more beneficiary. So in future we are going to see that such kind of transformation. Up till now whatever we are having at our home or in the premises, they are alternate current supplies or transmission lines with an ordinary conductors. So we are facing a quite big problem, big energy losses, but we are in the view of replacing all these things with the help of direct current grid with made up of superconductors. But for that we need, you know that we have already studied high temperature superconductor. So as a solution of this problem, we need a quite we can say more amount of high temperature superconductor, and that we'll see that we'll find it in a future. Same way, there is another small arrangement was carried out by Russian scientists. They have done one hybrid we can say transmission line, because all of a sudden we cannot change the whole thing. Up till now we were using a normal conductor as a transmission line, and we were using a alternate current method to transmit all this energy. But rather than that, if we are replacing it, so we cannot replace the whole part, but if we mix the two, or if we make the method with a superconductor as well as normal conductor both together, that is actually hybrid transmission lines we can set up. So in that case, in certain portion we will transmit with the superconductor, and that is also in terms of DC supply. But on the other side, we can say we can send normal supply available, alternate current, and with the conducting wire, normal conducting wire. For making such kind of hybrid superconducting grid, they have made a special kind of conductors, or we can say cables, in which they were passing a liquid hydrogen, and with the help of a low temperature they were able to convert that conducting wire within the cable in a superconducting state, and due to that they are not offering any kind of resistance. And for that they have generally used magnesium diboride. This is a composition of magnesium, and that is offering superconductivity at low temperature. It's quite low compared to the temperature over here in India we are having, but they are able to establish such kind of hybrid transmission line, and we hope as we'll get other superconductor which are showing superconductivity at higher temperature, whatever temperature we are having, about we can say 27 degree, more than 27 degrees Celsius right now over here in Ahmedabad or in India. So let's hope about 350 Kelvin, if we are getting superconductor more showing superconductivity more than 350 Kelvin, then in that case we are going to have such kind of hybrid transmission lines over here also in India. Now this is the another application. Rather than transmission and generation, we are having quite one big application, that is making a electromagnet with the help of electricity, that you already studied in lower standard. If we allow the current to pass through the material, then it is going to create a magnetic field also. You remember the Ostad's experiment started from there. This is the one important application of creating electromagnet and creating a magnetic field which is variable. With the help of permanent magnet also we can create a magnetic field, but it is permanent, which is constant, and we cannot change it. Electromagnet will offer quite good convenience in that we can change the strength of a magnetic field. We can make it zero also, and we can make it in a inverse manner, so we can change the direction of or polarity also. So that kind of thing can be done with the electromagnet. But electromagnet can create a current, create a magnetic field which is depending on as you know that current, cross sectional area, then the material which you are putting inside the material, that is core material. Such kind of things are making a difference in the creation of magnetic field. But if you want to make out a large magnetic field, then it is not possible with the normal electromagnet, because large current is if it is passing through the coil of that electromagnet, again the Joule effect will play a vital role in that, and it will heat up the thing and it will melt down the whole setup. So what to do in that case? We are having a superconducting magnet available, and generally with the we can say we can say saying super magnet is also another word used for that, synonyms, but it is not a synonym. It is a we can say a changed word that is accepted in a society. It's a superconducting magnet rather than super magnet. In superconducting magnet, what we are going to do? We are going to use superconducting material or conducting wire as a winding coil. So if we are using a ferromagnetic material as a core, and then we are winding a superconducting material as a coil on that, then in that case the current when passing the current through that, it will create a large magnetic field compared to the normal arrangement. And here, as we don't have to pass a large current for that, we can pass small current because resistance is almost zero or zero. So due to that, there won't be any heating effect, there won't be any hysteresis losses, there won't be any Joule effect. Such kind of losses they are avoided. But here what we need to do, we need to take care that the temperature of or ambient temperature of the coil that should remain smaller than the critical temperature. If it is going above that, then it is going to convert it into itself into normal conductor, and then again the losses will come into picture. With the help of normal magnet, what we can do, so if we use a normal magnet, electromagnet, to create a magnetic field, it will create a very small magnetic field. But if we use a electromagnet made up of superconductor, then it will create a quite large magnetic field, that is of several Teslas. And the comparison also given here, 1 Tesla is we can say 10,000 times more than the magnetic field created by Earth. Obviously Earth's magnetic field is very feeble, but if you want to create a large magnetic field for the certain application, then in that case we need to use superconductor to make out a coil, and then it is going to create a large magnetic field. Here the another one more material is also mentioned. The wire are often made up of niobium and titanium, that is NBTI. It's an alloy mixture of these two metals. They are generally used as a wire or superconducting material in the case of electromagnet made up of superconductor, superconducting electromagnets. In that case we are using such materials. If we go further, where are the such kind of applications available where we are using such kind of we can say strong super magnets or superconducting magnets? So it's not a just a talk, but Fermilab, at Fermilab it is already used or it is in use right now. So superconducting magnets, they are used there to create a quite large magnetic field. It's about 4.5 Tesla magnetic field which we want to create. For that they have set up a quite large arrangement. In a 7-meter long tube they have created magnet, and that the whole thing is set up into 6.2 kilometer periphery. That is actually accelerator is there, and the circumference of that is 6.2 kilometer, and they have arranged 774 segments, such kind of superconducting magnets over there, and along with that they have used 240 such kind of magnets to focus the beam. You have already studied the accelerator, that is cyclotron, if you remember, and in that case we were using a 2D shape arrangement, and within that we were putting a seeder which was creating a charge particle, and then as we change the polarity, or we can say polarity on the 2Ds with the help of RF coil, we were able to accelerate the charge particle. But to guide them, to restrict them within the small region, we need to have a magnetic field over there, and that kind of magnetic field is used over here in this kind of arrangement, that is the called Tevatron. Tevatron is the super magnet arrangement for accelerator or